So 285.2 multiplied by 33,000. Let's see what we get. We get 9.41 MVA, and this power, we are dealing with a three-phase system, and the difference between a three-phase and single phase system is root 3. So whatever we get here, we are going to multiply it by 1.732. Then we have 16.30, which is approximately um, um, 16.301 kVA. And if you want MVA, I mean, so, and if you want to convert it to kVA, which is what we have here, we have 16301 kVA. All right. So the power transformer is 15 MVA. As you can see, the capacity of the load flowing through this transformer is higher than 100%. This transformer is loaded on is over 100% loaded. So that's why this ETAP colored this as red, so that as a design engineer you will know that this loads is too much on the transformer, and find a way to either design a higher capacity transformer for this circuit, or you find a way to carry out load shedding on these feeders. Depends on your priority. Alright, so we have this cable. The current flowing through this cable is 855.6 amps. What this means is the capacity of the cable that we selected, I think, is 240 mm. You can see that even without checking the the current capacity for 240 mm, you should know that 855.6 amps is too much for that, for this 240 mm. That's why ETAP colored the cable, so that you know this is overloaded, which can actually damage the insulation of this cable. And once the insulation is damaged, short circuit will occur, and once short circuit occurs, it will cause system instability, and if there is no proper protection, the fault will cascade up to the transformer, from transformer to the grid. Hence we have system collapse. They said we should not be calling it system collapse again. They said it is now system disturbance. So that is that on this cable. We will try to, after explaining everything on this, we'll try to see how we can actually get rid of these red colors. All right. So this cable is overloaded. That's why we have it on red. And as we have said, we said load flow is actually used to know the voltage drop in a system before you actually carry out the project. So you can carry out the simulation and select your component and see how the system will behave in real life. So for this cable, there is a voltage drop of 413 volts. That's why, so from 11 kV is coming from this power transformer. The cable receives it, then it will drop 413 volts, then release the voltage to the bus. where we have 10,276 volts, and if you convert it to kV, we have 10.276 kV. So if you convert this to kV as well, we have 0.41 volts. All right. So if you sum this and this together, we are going to have 11 kV. All right. So that's why we are having this voltage at this level. And then this 11 kV bus is is overloaded as well, because I think there is a place to configure this bus as well, but probably the default current rating for this bus according to ETAP cannot carry 855.6 amps. That is why it's actually colored it as well. So you select a higher cross-sectional area for your bus such that it will be able to accommodate 855.6 amps. Alright, so let's try to confirm from the definition of a transformer. A transformer is a passive electrical device that transforms electrical power from one level to another without changing its operating frequency. So in essence, whatever transformation that is happening in a transformer, the power doesn't change. So let's try to confirm that statement. I think we've been able to confirm that the capacity at the primary side using this current and this voltage is 301 MVA. So let's try to confirm this as well. So this is the current at the 11 kV side and this is the voltage. So 855.6 multiplied by, if you could recall, the power in VA is equal to IV, which is the apparent power, multiplied by 10.276. We have 8,792,146.6. Then you multiply it by row 3, which is in 3-phase. Since we are dealing with a 3-phase system, this system is not a single phase system. So we have 15.276 278 MVA. Alright, you can see that we have at the primary side we have 16.3 MVA. At the secondary side we have 15.227 MVA. Why is it like that? From the definition I gave before now, we said a transformer is a passive electrical device. So transformer doesn't generate power, so it only takes whatever you give it, then release whatever it will take whatever you give it, then based on the number of turns that you've wound around the transformer, it will give out a particular secondary voltage. For this operation, transformer will take some of this power to do its work. It will take part of whatever you inject at the primary side to generate magnetic flux. So the difference of 16 and 15 MVA is because at the primary we have the higher MVA rating at the primary side, because it has captured both the losses, whatever the transformer uses to work, and the losses. It has captured it among the power rating at the primary side. So the secondary side doesn't capture the current used by the transformer to carry out the magnetic for the generation of the magnetic flux, and the losses, which is the core iron losses, I mean, which contains hysteresis and iron losses. All right. So at the bus we have 855.6 amps, and for each of the load it represents, we have the current for lump load 1, which has 362.8 amps, the second load 273.8 amps, the third load 219 amps. All right. So if you multiply this current by this, it will give you 6456 kVA. All right. So we have the voltage drop for this cable, which is 322 volts. Cable 8, same thing, we have the voltage drop. Cable 9, we have the voltage drop. All right, this is the current and voltage flowing on the load. All right, so I think we've been able to know the power flowing through each section of this component. And if you sum this 362.8, 273.8, 219 together, we should have something close to 855. Let's try to confirm that. Three 262.8 plus 273.8 plus 219, 855.6. As you can see, we have 255. If you sum the current on each load, that is the sum of current that you are going to have at this bus. That's KCL. All right. So let's try to see what we can actually do to bring out this red color on a power transformer. So there are two ways around it. It's either you increase the capacity of this transformer, or we open one of this load such that the sum of the load flowing through this transformer will get reduced. So to make it easier, let's try to before increasing the capacity of this transformer, let's try to open one of this breaker. That is the purpose of having a breaker on load, so that we'll be able to do load shedding without overloading the power transformer. So you click on edit position, then you right click on the breaker. You can see that the breaker is closed. Then you unmark it, then you can see that even ETAP has told us that it is now in open position. Then you go back to your load flow, then you click on PQ, run load flow. as you can see, the power transformer is no longer red colored because the load on it has reduced to 9 MVA against 16 point something that it was loaded before. You can see that the load on the power transformer has reduced drastically to 19.2 MVA. So that's one of the ways around um, 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 removing the overloaded stuffs on your power transformer. So what else can we do? Okay, all right. If, for example, all these loads are critical loads, like it's not something you. All these loads are very, very important. So you wouldn't want to open any of this load. So one of the ways around it is by increasing the capacity of the power transformer, since you've been able to know that the total load on our on of the sum of our load is 16 point something MVA. So you might want to change the rating of the power transformer to, let's say, 30 MVA. So you change the power rating here, you maintain every other informations, then you click on OK. The power transformer rating has changed from 15 to 30. Then you click on OK. Let's try to close this breaker back to service. Then it has been closed. Then you go back to PQ. Then you click on run load flow. As you can see, we've loaded this transformer. The initial breaker that was open has been closed, and the transformer is no longer giving us the red color. So let's try to return it back to 15 MV and see if it will change or not. 15. Click on OK, then run load flow. You can see the red color has returned back. So if you want to relieve your transformer, it's either you increase the capacity of the power transformer or you carry out load shedding. In such a situation where you cannot all your loads are critical, you cannot afford to carry out load shedding, then you recommend improving the capacity of your transformer. So let's try to do normal this thing. Is not highly recommended to carry out load shedding. Let's assume all our loads are critical, so let's improve it to 30 MVA, then click on OK, and here we have it. So we can see that, okay, let's try to see the rating of our cable. The rating of our cable is 400 mm. The rating of our cable is 400 mm for this level. Let's try to reduce the load by opening this, then let's do load flow. Let's see if this will have any effect on our cable. Yes, you can see that the cable 1 is no longer in red color because the amount of current flowing through the cable has been reduced. Alright, 210 amps, 210.9 amps is flowing through this cable. That is why, which is within the range of a 400 cable. That's why the red colored has been removed. And if you observe the voltage drop as well, I think it was around 400 and something volts. It has now reduced to 102 volts. So the voltage on this bus has increased to 10.915. If you sum this together, you have 11 kV. You have 11 kV. So one of the ways, one of the you can what we can actually deduce from this is one of the things that actually causes voltage drop is loading. By loading, increasing the load on a particular cable or a conductor, you are actually introducing voltage drop. There will be voltage. The more you increase the current, the more the voltage will drop, unless you are increasing the cross-sectional area of the cable as you are increasing your load. But if you maintain the same cross-sectional area for a cable and you are increasing the load, the voltage drop will continuously go higher based on your load. As you can see, immediately we open this breaker and this breaker, the bus voltage, the bus this, if you noticed, this bus is on red as well. But because the current rating of this load is not higher than the bus, that's why the color has been removed from red to black. It means everything now runs fine with this circuit. What this means is if you want to actually increase your if you actually want to run this type of load on this circuit, it means what we can actually deduce is you have to increase the capacity of your power transformer, increase the cross-sectional area of this cable. If you can recall, we used 240 mm. So you increase the current amperage capacity of this bus as well. And I think these cables doesn't give them red color, so it means the cross-sectional area we selected for this cable, we designed for this cable is okay. So I think we've been able to make some point out of this load flow, which is and I believe if you have any circuits to design, or as a power system engineer you have a project to work on, you can actually do a load flow of the whole circuit such that you'll be able to determine the size of conductors that you need, the rating of the power transformer, the bus, the breaker, and what have you. So we've been able to trash load flow on ETAP using this simple circuit. So we've been able to get the voltage drop, the current rating, the kVA rating of the bus voltage, and voltage drop at each of the cables. Before the next video, keep watching, keep learning.